Hello, and thanks for joining me again. And yeah, we've got a bit of an interesting one today. It's finally time that I took a little look at a thing called the Polaris paper. So within Azure Synapse, we've just got a SQL Data Warehouse, and that's got this whole history of distributed scalar engines within a fixed cluster. And we've got this brand new thing called Serverless SQL. And we've done a few videos on Serverless SQL and how that fits together and how you use it. We haven't really talked about what happens under the hood. Now, as part of the whole build of Synapse and the part of kind of making, I guess, SQL work at that kind of instant serverless distributed querying engine kind of way, they had to make a whole load of changes to how SQL Server works. And that's one of the important things. It's still using SQL Server under the hood. So how do you take like a single box SQL Server or even a massively parallel processing engine such as SQL Data Warehouse, as was, and turn that into a super expanding cloud scale distributed querying engine that works over lakes as well as in a relational database? And that's what this Polaris engine is. So VLDB, again, kind of a very large database conference, very academic conference, very kind of research oriented. There is a paper the Microsoft guys submitted to VLDB around Polaris, around how this new engine they've built to enable serverless SQL and to enable some of the newer stuff in SQL Pools, and how that works. So we're going to step through the paper. I've pulled out a couple of interesting things, a couple of things that I certainly find interesting. And it's very weird looking at this coming from a Spark background. Because I do a lot of Spark, and reading a lot of this is like, yeah, that's how Spark works. But it's so crazy to think they've made it work, but with a SQL Server. So we'll take a look through, we'll pull out some interesting points, I'll share the link so you guys can go and have a read of the paper yourself. As always, do not forget to like and subscribe and let us know down in the comments what you think of the service, what you think of how they've done, if I've interpreted any of it wrong, because I have just skimmed through this paper, pulled out the stuff that's interesting to me. Be interesting to hear from you guys about what you think about this engine and what you think it means for how we work in the data space. So let's get started. Let's have a look. Firstly, you can just Google Polaris VLDB. It's not a secret hidden away paper. Didn't have to fight anyone to get hold of it. It is out there in public, in the open web. Don't pay for it. I found one or two places where they're kind of a paywall going, you too can get hold of academic papers. VLDB share all of their papers. So you've got the Polaris VLDB endowment, and this is the whole paper that I'm looking at today. So quick Google, I'll post the link anyway. But we're going to work through one I've made a few little highlights of. Okay, so this paper is the Polaris Distributed SQL Engine in Azure Synapse. So this is the thing they built behind Synapse to get it to work properly. And it's certainly interesting reading this because I did a run through the Databricks paper a little while ago when they talked about how Delta and kind of the Delta approach has enabled Lakehouse and all of those approaches. And there's so many similar things in here. So having a run through, there's a lot of terms that I'm not going to run through just now because we'll go in more detail. We'll be talking about things like cell data or data cells, how they're doing scale out versus kind of scale up, the service model, that's all the serverless thing, how they want that to work. For me, the most interesting was that little statement to the top saying, we believe that two approaches converging, relational SQL toolchain, so data movement, catalog, business analytics, and reporting, supported directly over diverse and large data sets stored in a lake. And that's kind of like what we've been banging on about for a while. I certainly talk a lot in the Spark side of things going, Spark is becoming more like a traditional relational database server. They're putting in governance and auditing and transactions and rollbacks and history and security and all those things that are just so common a garden in the relational database world. They are kind of new in the Spark side. And we've kind of seen the SQL side, the kind of the database side, kind of slowly taking a march towards the Spark side or the big data side. And it's a convergence. And we've seen that on several different ways. And it's kind of good that, this is being acknowledged up front from the SQL Server guys. They're like, you know what? It's all going the same direction. So big data tools are getting more like traditional databases. Traditional databases are getting more like big data tools. There's a point in the middle where we're all trying to meet. And it's kind of like who's going to get there properly first. So Polaris is the latest Microsoft stab at saying, we've got there. This engine does both sides of that puzzle. Okay, so as I said, we'll go through some of these kind of key points as we go. as usual, in VLDB, you need to call out, here are some of the other things that we're similar to. So they talk a little bit about Spark, about Athena and BigQuery, about Snowflake and Redshift, and some of the other competitors, and how some of the unique points that they're pulling out in Synapse, how they're seen in some of those other systems, which just makes sense. There's no point pretending a lot of this stuff is new, because a lot of it is openly inspired. You know, when we talk about this has been inspired by big data technologies, those big data technologies we're talking about are Athena and Spark and traditional Hadoop and all of the things that are out there anyway, and it would be foolish not to acknowledge that. So they do got to go through and mention some of these different elements, where that comes from, and mark back to it. I mean, for me, there's some things in here which are claimed as this is a novel new approach. It's like, no, that's just how things work. But it's very new for SQL Server. So let's have another run through, again, kind of talking about those existing things, and then we can start talking about the new stuff. So separation of storage and compute. Now that is an age-old no-brainer when we get to cloud computing now. You know, it's always been expensive to take all your data, put it into compute, do some stuff, and then take your data, pull it out. So the more you can just say, I want to turn my service off and still access my data. That's a fundamental of why we use lakes. And that's obviously something that's missing in the kind of the dedicated SQL pools, the kind of SQL data warehouse. You have to have it turned on to access your data. Meaning you need to be paying for a big, massively parallel compute engine if you just want to do a quick query. So going down the path of separation of storage compute just makes entire sense. And the bit that kind of the point they're making here, about this little diagram, is actually saying, there's three different layers. So sure, separating storage compute, no brainer, we know that. But actually where people need to be heading is separating storage, transactions, and metadata from compute. And so it doesn't matter, we don't need to have a service turned on to be able to know if we're in the middle of a transaction, or to be able to know the transaction history of our data. And there's definitely an interesting approach that they're making here. Now, obviously, I'm going to argue in terms of what we're doing on the Spark side of things, that's just Delta. So the Delta file format, it has a transaction log baked into it. It has metadata baked into it. That is stored in the storage layer, not in the compute layer. And so basically, this is a separate approach to this. So whenever we're talking about that kind of metadata transactions, that kind of stuff, in the Synapse world, in Polaris, they're talking about storing that as a separate compute state, as a separate artifact. So you kind of have the kind of three different things of, I've got my storage layer, I've got my transactional layer, and then I've got my actual grunt compute that I'm applying to do some stuff. So definitely an interesting approach, definitely kind of interesting having a look at how that fits together. But certainly kind of, it's kind of, even so, it still kind of aligns with how we're thinking. So it kind of follows that path of going, you know what, compute is the expensive thing. And I want to store the minimum amount of stuff in the compute side. I want compute to just spin up, do a load of stuff, turn off, disappear, and I don't want to think about it. That's very much the path that Polaris is taking. Okay, so loads of things in here about kind of how they've done that, why they've gone down that path. For me, that kind of just makes sense. It's, stateless compute architectures. That is what we want. The compute should be entirely dumb. Turn on, do some stuff, turn off. We don't need to get back onto that same server. Next time I run a query, it can be an entirely different CPU that spins up, do a load of stuff, turn it off again. So, makes sense. Then we get onto data abstractions. So there's a lot in here about this concept called data cells. And they're kind of pushing it, saying, so we've got data that's held down on disk, and we need to actually sort of pull it out and kind of separate from what we're doing there. We need to abstract away from a file, from a directory, from a table of data, and work in a slightly different way. So they've come up with this concept called data cells. Essentially, chunks of data held across the life of a query. So you might kind of read up some data as 20 data cells. That requires some transformation and some joining, and then you'll have 10 data cells spat out. You'll do some aggregation and have 3 data cells, and then you'll write it out. And again, if you're coming from the Spark background, that's an RDD, that is a resilient distributed data set, and they're very similar concepts. So if I'm going off reading some data, I need to abstract away from what that data was into, I've just got chunks of data. I have some kind of block of data. In this case, they've called it a cell. Now, the main difference between what we know of as RDDs in the Spark world and similar concepts in many, many other big data tools is the idea that we've got two-dimensional breaking up of those cells. So coming from the MPP world, distribution is a very important concept. So the idea of saying, I want to break up my data, and I want to make sure that when it's broken up, it's organized into blocks according to these values, a hash value or round robin or replicated. These terms that you will be very familiar with if you're coming from the SQL data warehouse side of things, dedicated SQL pools. And then you've got partitioning. So then you've got the physical breaking up of that data. Now, when we were talking about SQL data warehouse, that's incredibly important for saying, I've got my 60 distribution, I've got my fixed number of different buckets, and I need to tell it how to spread the data across that for efficient querying, because I want to make sure all 60 distributions are included in every query, so I get the maximum amount of my parallelism that I'm already paying for. Now, obviously this concept changes because we're no longer tied to 60 distributions. We're not going to have 60 data cells every time we query things. So the idea of distribution is very different. But we still have this idea saying, I want to spread my data out so it's logically organized in such a manner. And then within each of those different kind of buckets of organized data, I might then want to split it up into partitions. So spread it out according to one key, partition it according to another key, and that will actually change and influence the number of cells that we have. Now, if we're in Spark world, we'd kind of normally that's all partitioning to us. That's all just partitioned by these two columns, and it'll just break down into a certain number of columns. Won't necessarily force it to distribute in such a way, unless we get into some of the deeper elements. So it's definitely interesting that from the get-go, the way they're defining cells is this two-factor, this kind of hash distributions and the partitioning functions, tying those together into that kind of one concept of knowing how data is spread and how data is chopped up to build out these efficient queries. And it's still just RDDs, kinda, with a different name, spread out differently. But still, good. I'm happy that it's working in a very similar way that I'm familiar to. I'm happy that they're talking about a common language in big data. Certainly I would be very upset if they'd got an entirely different approach and the whole concept of parallelism was a completely alien thing that we work with. The fact that they're saying, break your data into chunks, organize those chunks in a certain way, and then we can organize work around those kind of reusable chunks of data. Cool, great, get it. Okay, so we're then talking about the way they allocate that to compute is all about saying, okay, so you, Mr. Compute Server, I've got 10 compute servers, 1,000 compute servers, whatever it happens to be. You take that bunch of data cells, you take that bunch of data cells, you take that bunch of data cells, do your processing, and then carry on. And that's exactly how we normally work with big data tools. So all good, makes a lot of sense. They pull out certain things. They pull out kind of to do with ADLS, Fido, Delta. It's interesting to pull out Delta because it's not supported in Synapse yet, but we'll see. Okay, then they talk a lot in detail about how they do this mapping of cells to compute, how they decide actually, you, Mr. Compute Task, you're going to have this bunch of cells. And the kind of the data movement engine, the distribution engine from SQL Data Warehouse, you can kind of see there is elements of that in here. So it's all doing things like I'm joining between two tables. Now they're both distributed based on this key, therefore I can just join them directly because the data cells that relate to one side of that query and the data cells that relate to the other side, if they're distributed via the same key, then both of those cells are going to reside on the same block of compute, meaning they're going to be able to join together. That's kind of where they're going in terms of how this query is organized. And then we've got several different elements that go into saying, if they're not distributed in the same way, and they need to turn one into the same distribution, then they generate extra tasks for that. Now, essentially, this is what we know and love in Sparkland as a shuffle. So if we're having to do any certain bits of compute, a shuffle happens, and in Spark parlance, that means it kind of breaks the data up, changes the partitioning structure, brings it back onto the workers ordered via in a different state, and then performs your query. Now, a lot of what they're doing here is, one, distributing to avoid shuffles, if they can, avoid data movement, and two, kind of laying out the different patterns, the different paths you can go if you can't avoid a shuffle and you need to do some kind of bringing the data together. And again, so lots of things aren't that different to how we used to working. And it sits right in the middle of, if you're used to SQL Data Warehouse with its various different data movement operators, various different ways it would do shuffles, and you're used to Spark in terms of narrow and wide transformations and kind of what it would do when you're doing a repartition or a coalesce and those different ideas. This is kind of a bringing together of those ideas. So talking about how it does this redistribution of data cells within an object as a precursor to being able to do a task, yeah, makes sense if you're used to that kind of way of thinking. If this is the first time you're ever coming across the idea of broken up chunks of data, how they're distributed across compute, having to change the distribution of data in order to satisfy query parameters, yeah, this is kind of crazy. There's a lot in here which is going to be fairly hard to pick up. So it kind of depends on your background as to how crazy some of this stuff is. So one of the big things, obviously, so this is all driven by this thing they're calling the DQQ, the Distributed Query Optimizer, DQO. So essentially, they've broken up several of their traditional engines, built new versions of those engines to manage things like this. So it's not just direct lift and shift of any of the SQL Data Warehouse stuff. A lot of it is new implementation to think around these things, inspired by some of those ideas, inspired by some ideas from big data tools on the site, which is interesting, and they go fairly deep into kind of what the different paths can be. And then they've got this idea of tasks and task templates. So essentially, by having a look at, in a broad sense, I've got some data here, I've got some data here, both are broken into cells. To bring that together, I've got these precursor tasks, and then this is what I need to end up with. You can get this idea of, well, this is how many cells I have, therefore this is how many bits of compute I need to do. And again, similar to if we're talking about Spark, we've got a job, we've got stages, and we've got tasks within those stages. This is a very similar idea of saying, trying to work out how many bits of processing, how many chunks of work do I have to do based on how many chunks of data I have and how many steps those chunks of data need to go through. Again, this does kind of make sense. It's kind of very familiar. So they're building out this direct data cyclic graphs, essentially kind of a chain of related bits of work. So they have kind of this whole execution graph of what needs to happen. They go into the detail about how that works and kind of how that kind of is planned and how it's scheduled later on. And they get this whole idea of kind of building up the difference between a query plan and a query task DAG. So the query plan might have several different logical steps going, well, we're going to do a nested loop here, we're going to do a distributed data movement here, we're going to do a join here, all those different things that you'd normally see in a SQL execution plan. But actually the big fundamental difference they're saying is actually, although there may be several different components in the execution plan so you can see what it's going through, we won't be able to do several of those at once. So it's going through an intelligent optimizer to pull and say, just because the query plan has 10 steps, maybe we can achieve steps 2 and 3 and 4 at once via a single bit of compute, and then steps 7 and 8 at once. So actually our task DAG tends to be a lot more optimized than our original query plan. So query plan, what are the actual bits of work? Task plan is, what are the chunks of compute I need to do to achieve that? Which, again, similar to a kind of Spark, if you look at the SQL engine, the SQL DAG that you get on the back of a SQL query in Spark, you'll get kind of these, this is my stage, inside that stage, here's what I'm going through. And it's the same kind of idea, different parlance for it, but essentially break things up into all the different bits of work, consolidate the work that can be done in a single bit of data movement, move data, do work, move data, do more work, minimize the number of move datas that you're doing to get the most efficient query. Kind of what we're talking about. Now, the interesting thing in terms of how they're then doing that is, whereas in Sparkland, what we're talking about is we normally have a fixed number of workers. We might auto scale, but our workers are of a set size. So we might have a, 8 core, 8 gig RAM box, and then I might get some more of those same workers. One of the things that they're talking about here in terms of the SQL Server scale up is actually if they look at that task and go, oh, well, that's a bit chunky, that's not going to spread efficiently across my SQL Server workers, I can scale up for that one bit of the task. So I can look at that grouping, the logical query task DAG, and go, I can do those bits on fairly small little SQL servers. That one I need a chunkier one for, and then I can spread it out to smaller ones. And because of some of the parts about how SQL Server can scale up, they can actually do that a little bit more efficiently. So inside that query DAG, inside that breakdown of work, inside how all that stuff works, there's some really interesting stuff about how they're managing to not have this flat, all bits of work are done in the same way. And again, I've not dug too deep inside there, but it's certainly sort of an interesting thing to kind of go, not all stages are equal in Spark parlance. Okay, when we talk about orchestration, obviously kind of, this is going to, so it's because Polaris is behind SQL Serverless, and SQL Serverless is meant to be just this insanely fast reactive thing. We've got to think of this as a gigantic beast that's serving not just my queries, but queries of everyone in my region. And so the whole idea of this kind of massive scale out orchestrator just doing a ton of different work at all time, the execution orchestration is a huge problem. So you can imagine how much they had to kind of go through and figure out how do you fit all these different competing workloads into one finite set of compute, which is interesting. And again, a lot of that kind of idea. So they've got this kind of concept of task templates and tasks. And I'm kind of just in my head translating that into stages and tasks, kinda. And there's some detail in it. They talk about the different kind of state of it. So very Spark friendly in my mind. They're talking about, a task is a given bit of work to do on a set amount of data cells given to a ephemeral bit of compute. And that to me makes entire sense. So a worker, point it to some RDDs, tell it this stage and task it needs to do on those RDDs, it'll do those work. If that goes down, just apply those same RDDs and those same tasks to a different Spark worker. That's kind of a similar way of working. So the whole idea of breaking down your query execution, you'll run this big SQL statement into, here's my individual blocks of work. And those blocks of work apply to individual data cells, chunks of data, so that you can say, if one of the SQL servers as part of that goes down, I can just bundle up that bit of work and say, well, just give it to a different one. But I'm not going to stop my query. I'm not going to error because one part of my massively parallel compute fell over. Just take that same blueprint of work, give it to someone else, and we just keep going. So that whole way of being able to break up the work into repeatable, transportable chunks of work just makes entire sense when we're talking about big data. Because the more services you spread of things, the more servers that you have involved in your query, the more likely one of them is going to die. It's going to blow up. Something's going to happen. When you get into tens of worker nodes, you're like, ooh, something could happen. When you talk about hundreds, something's probably going to happen. When you talk about tens of thousands, something is definitely going to blow up during the life of that query. And you wanted to go, yeah, that's no problem. Carry on. That's how it should work for large-scale distributed queries. So they go through some of the detail of how they've implemented that. We've got this idea of task precedence, task blocking, and the details of how they bring those things together. So obviously, if I've got a particular task template, so a particular group of tasks that I need to achieve, and that is blocked by an earlier bit of work, then there's a whole thing of breaking that down, waiting until it's done, having the state of these different tasks, and that needs management. And there's a whole pain about building distributed engines of working out of all of my thousands of different tasks I've got that are dependent on one another, what's the smartest way to actually order that? How do I prioritize that workload and go, but if I do those first, that unblocks that set of work. But if I do that, that finishes that query. I can give those results back, and then I can get on with that. And that's that whole juggling of different workloads in order to get people the data that they need and successfully unblock other bits of work. So they talk about how they actually manage to do that, the different states a task can go into, and how they juggle those different components within a particular query. Again, interesting to see. Doesn't tell us that much about what we need to know in terms of building queries or writing queries, but certainly helps explain some of the challenges that they have to be aware of when building this stuff. And again, all the things that they're trying to do. So being able to be aware of blockers and dependencies, so you don't have a query that's just forever in a blocked state. Reliable execution, if something blows up, we need to be able to actually go back and redo it. It needs to work the same way and get the same results if you run the same query twice. Makes sense. Reproducibility at scale. You write a query and then run the same query with 10 times the data. The same query should be able to run on a few meg of data, gig of data, a petabyte of data. You should be able to actually sort of scale out these things and work in similar ways and kind of let the engine figure out how it works on that stuff under the hood. And again, concurrency is the biggest thing in serverless SQL because they've got to manage all of this stuff. In terms of workload aware stuff, again, a lot of that is to do with how they're prioritizing things. And that thing I mentioned of how do they decide which bit they do first? Is it first in, first out? Is it sorted by the resource demand? So actually, I've got a massive query that's just come in, but someone just snuck in a really small little select. We can do that first, get that out of the way so they get the results, and then we'll worry about the big thing. Is that kind of just being aware of the scale of each of the different queries sat in that queue. And there's sort of by proximity to root, which is, so this chunk of work, this stage, this task template, how close is it to actually being returning results? So if I'm doing a little bit of precursor work that's just getting data ready to be executed by other parts of that chain of query, or if I'm doing my final results aggregation to return the results, I can prioritize that end piece because that's going to result in someone getting their data. So that kind of, how close is it to finishing the query to get the user the end results, or is it just a part of that puzzle? And so prioritizing depending on these floating bits, who asked for it first, how big are they asking for, how close is this thing to finishing compared to other parts in that puzzle? Obviously, there's a challenge there in terms of figuring out how those things pull together. Okay, we then talk a little bit more about how they've actually sort of built our architecture behind it, how they're achieving this. So a little bit more about scheduling, about the test templates to finish that off. The service architecture is, it's definitely interesting that a lot of these concepts we're talking about are fairly familiar if you're coming from a big data background. Certainly coming from Spark, we're talking about drivers and workers, and on those workers, I've got an available number of slots, and I'm taking a query and breaking it down into jobs and stages of tasks. That's all absolutely makes sense. And it's really interesting to look at this and say, so how have they actually built this service? Well, they've got a centralized metadata from transactions. That's kind of what I'm saying. So unlike Sparky World, where we're saying with Delta Lake, we're putting the transaction or putting a metadata down at the storage layer. With Synapse, they're saying, well, actually, we're just going to have a centralized bit because we can separate that from our compute nodes, but it's still going to live on some kind of compute. So essentially, fancy, scaled, efficient SQLDB is sitting, managing our metadata and our kind of transactions, not putting it down at the storage layer. And then for doing the actual query execution, for doing our actual workload management, we've got this kind of three-step thing. We've got the SQL Server front end, essentially a driver, something that takes our query, passes it to a query processor. Because that's kind of the user serving layer. We've got that middle bit, the distributed query processor, which is the whole workload scheduler. It's the figuring out how many data cells do I need for this? How many workers do I need to spread my data cells across? How do I prioritize that compared to other bits of work? And then I've got the compute service, which is entirely scalable, as many as I need, whatever's going on behind the scenes to allocate those. And it's interesting that those compute servers are just SQL servers. Just SQL servers. They are SQL servers. They've got the full rich maturity of the SQL Server engine. But it's certainly interesting seeing that, obviously, comparing to Spark, compared to things where those compute engines are so light. They are so made out of, kind of a currently little Java virtual machine with a Spark app, which is kind of not a huge thing to have in it. So you can spin them up fairly quickly. But it's interesting that bank of Azure SQL DBs, essentially, that are spun up and just dynamically allocated. Essentially, it's like doing elastic pool over thousands and thousands of people. Okay. So then inside there, it talks a little bit more about how that's working. Again, breaking it down into that each of our SQL DBs, we'll talk about an execution service as a SQL Server instance. So something that is managing which tasks have I been given, how am I working through those tasks, how have I reported back into the state of those tasks, and how have I moved data around. So that's kind of, the execution service, and then the SQL Server sitting next to it of the actual SQL Server engine, doing the query, for that individual task, working out the actual SQL execution plan, running the SQL query, returning the results, doing normal SQL things inside it. Super interesting. And then data. So we've got this thing called a data channel. Now, with all SQL Data Warehouse, you've got the data movement service, the DMS. So you have a dedicated service that is just moving data around, going, oh, that needs a broadcast. Okay, well, I'll broadcast that out. That needs a shuffle. Okay, I'll move that data around. And it's essentially kind of this backbone infrastructure, just shuffling data between your different compute services. And this is a similar idea, right? So anytime we're looking at those data cells and going, well, I need to move data cells, I need to transfer data cells between these compute services, you've got that similar idea running in the background. So again, not crazy in terms of how we're thinking about things. Driver workers, and then an overall management service. That's kind of straightforward big data architecture. That's kind of what we're expecting. Just super, super interesting that it's been achieved with SQL Server. So it is just SQL servers, but built into a very, very scalable, stateless format. A little bit about some of the failover scenarios, about kind of saying, kind of if it was going slow with so many tasks per worker, just give the tasks out to more workers, add more compute to it. Things like failover, so being able to go, that worker's dying, just take the same task templates that were assigned to that worker, put it onto a different bit of compute. Sorry, I'm going to keep calling things Spark things, sorry. I'm being able to kind of move things around, seeing that one particular part of that query, one particular task/task template is taking too long, just go, oh, cool. Take some of the task and give it to another worker and spread the work out. All very familiar in the parallel workload world. So just talking through how they've achieved some of that, talking through why they've went, some of the kind of the ways that they've gone. But again, a lot of those things are fairly familiar in the big data world. So, separation of state and compute, abstraction of data set into cells. That's how they're achieving this elastic querying. Task inputs is defined in terms of cells. So I want to, this task needs these 3 data cells. Kind of makes sense what we do with RDDs. And orchestration using ephemeral compute. All entirely makes sense. That's how they're getting resilience to failure. It's how they're getting the managing skew. Again, that's the redistribution of tasks across compute if they realize one particular part of it's taken too long. All entirely makes sense. As usual, there's a load of performance constraints, performance evaluation. So talking about the concurrency that they managed to do. And honestly, the concurrency that they're currently getting off the back of Polaris is insane. It is, you see some awesome stuff in terms of the data that they're getting out of it and their ability to, one, run very, very big queries across huge amounts of data, and 2, just run thousands and thousands of queries and manage that across. Now, similar, I would assume, to if we had a Spark engine that had that fixed number of nodes. The interesting part is because this is just based on a huge bank of available Azure SQL DBs, you worry less about cluster definition, you worry less about cluster size. That's kind of a Microsoft problem. They're saying, don't you worry about compute. Just tell us with the query and we'll figure out of all many available bits of compute, we'll just give it to some bits of that, do the work and give you the data back. So just kind of saying, the concept of the cloud as someone else's computer, rather than saying, well, actually, I know which of their computers I'm using. It's just that they've got thousands of computers. I don't care. Just do some of the work and then give me my results back. And because it's a SQL DB and because it's just sat there waiting for work already, it means we can do things very quickly and at scale. So definitely interesting in terms of how they managed to do that. Again, do advise just having a look through the details and reading out some of what they've managed to achieve with those performance results. No point me just reading that out to you. Okay, final part. So when they're looking at heterogeneous kind of data types, when they're looking at interesting, weird data types, that's the whole point of using a lake, right? The whole point of doing that is the ability to query across interesting, awkward file types. To query across CSVs, across Parquet, across JSON, across image files, video files. There's a whole wealth of weird and wonderful data sets that we want to see. And so they do talk about kind of reading Parquet, reading nested structures, reading CSVs, that kind of stuff. And they're getting great results in terms of their ability to query some of that stuff. I do disagree with some of their conclusions, I've got to say. So in the conclusions, they presented Polaris. So this is the new engine. So if you're using Synapse Serverless SQL, it's using Polaris. Don't think dedicated SQL Pools is using Polaris yet, but I'm assuming that's kind of something that we're going to be seeing. Those clusters are going to work in a slightly different way, going to diverge slightly from traditional SQL data warehouse. I assume, given they've built this thing. I don't know. But this claim, so they've built a new processing framework in Azure Synapse that seeks to support both big data and relational warehouse workloads, going beyond current systems of either kind in its flexibility and scalability. Oh, that's a big claim. So in terms of existing relational engines, its flexibility and scalability is insane. What you can achieve here because of how they've architected it using traditional big data approaches and they're harnessing the power of the SQL Server engine, absolutely. Huge things they've managed to achieve by this, which is awesome. To say it's more flexible than existing big data systems, I'd kind of challenge that. So certainly in terms of Synapse SQL currently, when if we're querying lake objects, we can query Parquet, CSV, and JSON. I'm afraid to say a lot of big data tools can query a hell of a lot more than that. Until we even see Delta supported by this, it's not that flexible. I'd want to see kind of this, because it's got this abstraction engine to build things into data cells and spread things out in that RDD style. I'd want to see that the same support for flat files. I'd want to see, it can read any kind of data file. Because once you've got this abstraction, once you've got this idea of a data cell or an RDD or a data chunk, call it what you will, you can say, read from the thing. I don't care what it is. Once you've abstracted into these data cells, it doesn't matter what the original format was. And so it's kind of sad that at the moment, the flexibility of this, how many different data sources you can actually tool it to, is a little bit limited. Now, it is an incredible foundation to build more flexibility into it. So the actual engine, the actual execution engine, what they've done with Polaris, again, heavily inspired by existing big data tools, actually sets them up for success in terms of doing a ton of stuff in future. It's not quite there yet. It's great. And, when you're in Synapse and you run a serverless pool query, the fact that it's kind of really snappy, quick execution over, a large amount of data in Parquet, properly nested with partitions, performs really well. Really impressive. I wouldn't say it is going beyond the flexibility of existing systems. But, maybe that's me being nitpicky. Maybe I'm being mean. Okay, and then having a look at other stuff, so yes, the workload task graph and the fact that it's global across everything going on that service is kind of insane. And yes, the fact that they're leveraging, decades of development of the SQL Server execution engine to make that faster, to make that better, to make its ability to do some of the hairier style of queries faster and better is fantastic. So it is really cool to see some of that stuff. And so it's just super exciting. It's exciting to see that as kind of a thing that's going to develop and grow and mature and turn into something that's even bigger and better than it currently is. Then obviously there's a load of references and there's tells you all the stuff that they've looked at. Obviously lots of things to do with Spark that they've built into it, other things with Hadoop and looking at things like Cassandra and Snowflake and big data and all that stuff. And that's the paper. So there's a whole load of stuff inside there, and it's definitely interesting. It's really weird. As someone who worked on Microsoft tools for quite a long time, it's really weird hearing essentially kind of the message from the SQL Server side of things, the SQL Server kind of program group and kind of all the kind of the work they're doing, basically coming out waving the big data flag, going, hey, we've got an idea. How about separation of storage and compute? How about abstraction into blocks of data and then distribution into ephemeral compute? It's like, yes, exactly. That is how so many people are working these days. Now, as I said, if you're coming from a traditional SQL Server world, if Synapse is your first foray into cloud computing and kind of certainly kind of modern data warehousing or any of that kind of stuff, this is a whole basket of crazy. It's a whole load of ideas and concepts and terminology that's probably entirely new to you. But I guess just be settled, be kind of comforted by the fact that this is a well-trodden path. A lot of the ideas, a lot of the approaches are so well known coming from Spark, coming from other big data systems. And it's just basically it's saying, let's take that way of working with the SQL Server engine behind it and the gigantic scale of Azure behind those things, put the three of them together into a new service. That's essentially what we've achieved here. Not to belittle what they've done, because they've done some crazy stuff in terms of how they built the execution engine and the distributed query engine. But that's kind of at a very, very almost kind of massively oversimplified point. But that's kind of what's been done. So take big data, breaking up of data, and kind of query execution and kind of parallelism concepts, make it run with a SQL server using a gigantic bank of ready Azure compute ready to go. Which, you know, when you spin up signups and you can just write a query over your lake and it just comes back with data instantly, it's worth it. It's pretty cool. So if you hear about Polaris, that's what Polaris is. If you hear about serverless SQL and you're like, how on earth does that even work? What's happening? Where's the thing that I'm paying for? That's what you're paying for. So when we're talking about kind of, you know, the payment being data read, that's actually the cost of going to your lake, pulling that data out into data cells, and then the movement of data around your distributed compute. That's what you're paying for. And it's kind of, it is an interesting way of thinking about it, because so many of the existing tools, you have to put a pin in those bits of compute in advance. You have to say, I want these 10 bits of compute, and I'm going to pay for them for the next 10 minutes while my query runs. And that's not the way this is working, because it'll be in that scheduler. Your particular query with your particular data cells will actually be jutting in and slotted in as a jigsaw amongst thousands of other queries that are going on at the same time. Definitely interesting stuff. So yeah, that is all for today. Again, let us know if you've got any questions. If you've misunderstood anything in there and you're like, no, this is far cooler than you think, please let me know in the comments. Please kind of get in touch. And yeah, otherwise, just have a go. Have a play with Synapse Serverless. It is really, really, really cool. But otherwise, have a good day.